All right, everyone. Welcome to another episode of the Twimmel AI podcast. I'm your host, Sam Charrington, and today I'm joined by Christos Luisos. Christos is an ML researcher at Qualcomm AI Research. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Christos, welcome to the podcast.
Thank you very much, Sam. It's great to be here.
I'm looking forward to jumping into our conversation. This episode is part of our iClear series, ICLR, and we'll be talking about one of your papers accepted at the conference on hyperparameter optimization through neural network partitioning, as well as some of the other accepted papers from your team and colleagues at Qualcomm. But before we do that, I'd love to hear a little bit about your background and how you came into the field of machine learning and AI.
Of course, of course. Yeah, originally I sort of come from Greece. That's where I did sort of my bachelor on computer science and telecommunications. And during the later years of my bachelor, that was the time when I sort of got first into touch with machine learning, and that was basically the point where I decided this is what I want to do. And yeah, after that I followed a master program here in the Netherlands in Amsterdam, where I basically met my future at that time kind of PhD advisor, Professor Max Walling. And after the master came the PhD here, and now, of course, here at Qualcomm AI Research in Amsterdam.
Got it. Got it. We've, of course, had Max on the show a couple of times now. What was your dissertation on?
So my dissertation was on sort of two things. The first one, so are you talking about the master dissertation or the PhD
The
dissertation?
PhD.
The
PhD.
PhD. Okay, yeah, yeah. The PhD was on. I mean, the title was called Probabilistic Reasoning for Uncertainty and Compression in Deep Learning, and that is a very long title of basically saying I work quite a lot with Bayesian neural networks, and we try to find several sort of applications of them. The first ones that we were looking into was how we can get sort of reliable uncertainty estimates on our predictions, sort of besides just getting some kind of answer or this kind of image needs to be a 2 or a 3, then how confident we are about that answer. And yeah, the second part was on sort of compression, like how can we use the fact that our parameters are uncertain to sort of better quantize them, better prune them, and so forth for efficiency purposes.
And is that area or those areas? Do those continue to be your focus at Qualcomm?
Of course, yeah. It is one of my focuses here on Qualcomm. I mean, Qualcomm deals quite a lot with efficiency, and yeah, that was like one of the main reasons also why I came here at Qualcomm AI Research in Netherlands, just because of like my research interests and expertise were very much aligned with those of Qualcomm.
And maybe take a step back and kind of tell us broadly about the areas that you focus on from a research perspective.
Yeah, so from a research perspective, I basically work on federated learning or distributed learning. So it has sort of two aspects. The sort of first one is, how can we do efficient learning, at scale while having access to data that are local on sort of edge devices. So the main premise on why you want to do that is that the data are private and therefore cannot leave the device. So what happens is that then the computation happens on device. Sort of, you have some kind of server that might be in the cloud, and that server sort of communicates a specific model to the edge devices. The edge devices do training, on their sort of private data, and then communicate model updates back to the server. So that's sort of the general pipeline of federated learning. And then in terms of like research, there's quite a lot of angles that you can you can pick up, just because it's sort of more of a system kind of approach. So we have done quite a lot of work on how, for example, you can efficiently communicate between the server and the clients via means of various compression schemes. How can you learn sparse models in this setting? The main benefit being that you can reduce both communication costs and also um, training costs on the edge device, especially since the edge devices are sort of hardware constrained. We've looked a little bit into differential privacy and how can that sort of combine with compression. Um, and recently, like our now iClear paper on how we can do efficient hyperparameter optimization in this setting.
Yeah, talk a little bit about how hyperparameter optimization is connected to that broader range of topics that you just mentioned.
Yeah, of course. Sort of the main premise of why we want to do hyperparameter optimization is, of course, neural networks have quite a lot of them, and if you don't sort of set them right, sometimes your performance is not up for the task. Now, the main problem is that in federated learning, sort of doing multiple training runs is not always desirable. First of all, you have to spend kind of more communication costs and more training costs at the edge, which is usually not very desirable. And besides that, every sort of new training run also spends more privacy if you look at it from that perspective.
Meaning, traditionally, when you're training a neural network, you're optimizing hyperparameters by just doing the training process over and over and over again, and that's less desirable on a edge type of device. Both for hadn't thought about. I imagine that you'd have the communication overhead, and you'd also be in many instances draining a battery by trying to do training locally. I had not thought about spending your privacy budget with differential privacy types of applications. That's an interesting one.
Exactly, exactly. Yeah, the point is that every time you communicate something about your data, you reveal something about your data. So eventually, if you do it enough times, you basically spend most of your privacy budget. Yeah, and exactly as you said, like traditionally, like random search, grid search, these things are not very desirable in federated learning.
Okay, interesting. So that's the broad motivation. How did you frame the problem for the paper?
Yeah, so basically how we framed it is we took like a lot of inspiration from marginal likelihood type of approaches. Sort of marginal likelihood is a specific technique that you can do when you have a Bayesian model where you can sort of optimize hyperparameters while sort of treating the likelihood of the data after you have marginalized all of the parameters. Sort of the main thing is that this kind of objective can be decomposed into a specific manner, which is, you can think of it as basically the learning speed of a specific model, where the kind of intuition is that you basically measures how well a model trained on a specific subset of data generalizes to sort of other subsets of data. And that kind of intuition is then used to optimize the hyperparameters. Now, the main challenge is that computing this marginal likelihood is usually intractable because it requires you to sort of integrate over all possible parameter configurations that you have. If you try to apply this on a neural network setting, that's obviously infeasible. But basically, we can still take inspiration from that kind of objective, and then based on that, we sort of devised like a practical kind of algorithm that simulates such kind of idea. Um, and yeah, how it works is that assume that we have a specific kind of data set. We can split it into k parts, and similarly, we have access to a specific model, neural network. We can again partition that neural network into k parts, into k subnetworks, if you'd like. And then basically how we do training, the parameters for of those networks is that the each subnetwork only sees a subset of the full data set. It sort of never sees the full data set. And in doing that, the nice thing is that then you can use the parts of the data set that you haven't really seen, for a specific subnetwork as sort of validation data, or like data where you can measure how well does that subnetwork generalize. And then you can use that as a learning signal for your hyperparameters.
And are these subnetworks? Are they architecturally defined, like a layer is a subnet or something like that, or are they kind of randomly defined? Or tell us about how they are defined.
So what we do is we do the simplest thing possible. So we randomly select a subset of parameters, and we treat that as one specific subnetwork. And in order to ensure that this random subset that you select, of course, goes from input up until the output, we sort of randomly select a subset of parameters for each layer, and concatenate all of those and treat that as the one subnetwork. And these kind of subnetworks are sort of chosen. Well, I guess the parameter partitions are, of course, non-overlapping. Um, but one of the main things that we do is that, let's say if you have two subnetworks, your first subnetwork is sort of trained on the first chunk of data, but then the second subnetwork, from the sort of marginal likelihood perspective, it can be trained on both the second chunk of data and also the first chunk of data. And to basically simulate that effect in our algorithm, what we do is we reuse the subnetwork that was trained on the first part of data as part of the subnetwork trained on the second part of data. So essentially, that subnetwork can act as some kind of information stored about the first chunk of data when you are optimizing the second chunk of data. So you don't really start from zero, more or less.
Does that mean that if you've got k subnets, that the first subnet is a superset of the zeroth and the second is a superset of the first, and so on?
Exactly. And in the end, like the last subnetwork is the subnetwork is basically is the full network. It basically has all of them, and that subnetwork has seen all of the data, and that is the network we use to make like any predictions for downstream tasks.
And so does that mean that that validation is better for the smaller subnets and less good for the, as you get to the larger subnets?
Yeah, so basically on the higher up the chain, so to speak, that you go, then the you have, um, sort of, I guess, you condition on more data, and therefore the effect of the validation data sort of becomes less. Sort of the sort of validation data at the lower end of the chain are those that sort of govern more, I guess, the sort of how the hyperparameters evolve. um, and that's also an artifact of this kind of learning speed perspective. So from the learning speed perspective, like the best kind of parameters are those that allow the neural network to generalize quickly after seeing a few pieces of data.
You mentioned that you define these subnets by kind of the simple random approach. How do you split the data set?
We have experiments in our work where we both do this thing for centralized training. So let's say that you had all of the data centrally, um, and then what we do is we basically split that data set into kind of KIID partitions randomly again. But the main kind of one of the main motivations for our work was federated learning, and the point being that there the data are sort of naturally partitioned, because each kind of device that participates in training has a specific chunk of data. And then how we construct sort of these partitions is by sort of randomly picking clients or edge devices and grouping them together, and then that group is sort of one specific kind of data chunk.
Ah, got it. So you, on the data set side, you're also splitting into K as well, but that K is made up of an aggregate of data from across the different devices.
Exactly. Again, it's sort of non-overlapping split. Yeah.
Yeah, yeah. And I'm imagining that maybe right now this is you're doing some kind of simple aggregation, but maybe in the future you might want to do kind of topology aware aggregation of these edge devices so that you're minimizing latencies and things like that?
Yeah. That's a very good question. Yeah, there's a lot of ways on how can one improve. You could argue if what you want to improve is like speed, how quickly do you train? Then yeah, you could sort of organize that it's kind of data cluster is sort of basically devices that have you know uh, similar latency to the server so that they all communicate quickly. Another thing that you could optimize for is that this subset of devices that you select or that you cluster sort of collectively have an IID partition of the data of the overall data distribution.
So that would optimize for privacy.
Privacy and most importantly, sort of gradient or like how quickly will it be able to optimize, because then getting a sort of gradient from this kind of subset will be similar to a gradient you would have gotten if you randomly sampled your full data set, so to speak.
Interesting, interesting. So what type of data did you use for developing the system and for benchmarking?
Yeah, I mean, we for this we basically followed like prior work, especially most importantly like prior work that uses sort of marginal likelihood type of approaches to like optimize specific hyperparameters. So that being said, it's mostly kind of vision type of use cases. So we had for example, C410. Um, we had Tiny ImageNet, and we had some experiments on sort of MNIST variants, and most importantly, like one of the set of hyperparameters that we optimize. So now that goes a little bit more into detail. There is parameters of affine augmentations, and sort of a natural like a way to see if the parameters of the affine augmentation that you learn make sense is to somehow transform your data set in a way that these affine augmentations make sense. So to give you an example, we had two kind of data sets from prior work, which is like rotated C410 and sort of rotated MNIST. And what those data sets are is that we apply some kind of rotation to the actual image, and then still maintain the same label. And then if you train while optimizing this affine kind of augmentation parameters, what you ideally want is that you do recover somehow the rotation that happens, because if you do, you sort of undo that effect that you did on your transformed data.
And so is this optimization, you mentioned the motivation here is to get away from multiple training iterations to do hyperparameter optimization. Is this a one step process or are there still multiple steps?
Yeah, so how we do is we do all of this throughout training in an alternating manner. Sort of we have the sub networks, and then let's say that you pick your sort of clients that will participate in training. Then these clients are sort of allowed to optimize a specific subnetwork each. So what they do is they get all of the subnetworks, they optimize the subnetworks, that the parameters of the subnetworks that they can optimize on their local data. And then besides sort of these fine-tuned subnetworks, what they also communicate is the gradient with respect to the hyperparameters when they used basically subnetworks that they cannot train on. So collectively gathering both of these things, what happens is that you do a single gradient step on the parameters of the subnetworks, and based on that, then you do another gradient step with the hyperparameters for the hyperparameters condition, the subnetworks that you have.
But iteratively through the training process as opposed to the first sequentially.
Exactly. And one of the nice things if you that happen in the federated setting is that overall, despite the fact that we optimize both parameters and hyperparameters jointly, our communication costs, like cumulative communication costs, actually go down compared to the if you didn't optimize any hyperparameters, and that is mostly due to the kind of partitioning that we do for the network. Sort of its client doesn't need to communicate an update on the full network. Its client only communicates an update on the sub network that it can train on, and the gradient with respect to the hyperparameters, which usually the hyperparameters are just a handful.
Can you talk a little bit about how you benchmark performance, how you benchmark the system overall?
I mean, the primary kind of performance check we had was just accuracy on some kind of test set. One interesting point is that if you do this kind of rotated versions of existing datasets that I talked about, if you do not learn like a proper augmentation policy, and that could be, for example, rotating image according to the rotation that exists in the dataset, your accuracy will suffer. So, for example, like the baseline would be, okay, we have some kind of specific network that doesn't do any augmentation, gets performance A, but then we can learn that augmentation with our technique, and then we get performance B, where of course B is larger than A.
And in that case, you're considering the augmentation to be a hyperparameter of the network.
Exactly. So then the augmentation is sort of trained such that a sub network trained on the first chunk of data generalizes well to other chunks of data, and so forth. And in this kind of rotated case, like one way to do that is to actually learn to rotate the image itself while you augment.
And in this augmentation case, is there a single hyperparameter, some single rotation value that's applied to all of the images, or are there, is it a vector? Are there multiple directions?
Yeah, so basically it's a vector. What we optimize that determines, how much do we sear, how much do we translate, how much do we rotate the image in both coordinates, and that vector is basically global. So each kind of sample is sort of randomly augmented according to that vector. Of course, the augmentation will not be exactly the same because you draw a different randomness for each point, but sort of the augmentation strategy overall is shared across all of the data points.
Awesome, awesome. And then in terms of initialization, are you doing anything special there?
Yeah, so that turned out to be like an important point. So the thing is, how do you define these subnetworks, right? So you could argue that you get sort of a subnetwork and you start from zero initialization. So um, what we did is that let's say basically zero initialization for the parameters that do not participate in training. But it turns out that at least empirically that was suboptimal. And sort of what we did is we randomly initialized the network, and then a subnetwork is basically a network where you optimize some parameters, and the other set of parameters that you not optimize are set to their initial random values. And that turns out empirically to work much better compared to, let's say, setting zero for the parameters that you do not optimize, like getting a sparse sort of kind of subnetwork.
Did you expect it to be the other way around? Did you expect that sparsity would have some characteristic that the network could take advantage of?
Ideally, like sparsity would have been nice more from the perspective of efficiency, because you do not really need to store those parameters in memory, or depending how your sparsity is defined, maybe you can also avoid doing some of the computation. um, Whereas if you sort of don't have that sparsity and you just have them on the initial values, you still have to do everything essentially in terms of computation. So from that perspective, it would have been nice, but empirically, it seems that we cannot get away, at least for now. Who knows? Maybe future research shows that we can get away with it.
And what about the k parameter that you use, which is itself a hyperparameter? How do you choose that?
Indeed. Yeah, we. The thing is that we don't really have a good answer for that, unfortunately. So,
You
what
saw.
we do, yeah, exactly. So one good thing is that we did an ablation study on that, and of course, there is some effect, but it doesn't seem to be significant. So I mean, if you really want to squeeze out the best possible performance, then that is something that you need to optimize. But if you go with something reasonable, let's say, two, three, or four kind of sub networks and data partitions, and you sort of assign like parameter counts and data points appropriately, then that kind of strategy generalizes reasonably well across all of the different settings that we considered. Yeah, but I mean, having said that, ideally, I mean, this is a paper about hyperparameter optimization, so we would want eventually to automate that hyperparameter as well.
Yeah. Do you envision a way to do it kind of within the same process, or is it kind of by definition have to be a separate optimization step?
Yeah. Yeah, well, I mean, we are thinking different things. You could maybe it's kind of hard to tell. So the good thing is that this kind of hyperparameter optimization method is orthogonal to other kind of hyperparameter optimization methods you can do. So sort of, for example, in the centralized setting, you could combine this kind of training method with another hyperparameter optimization method that optimizes over k. Um, let's say, having said that, that is not sort of intuitively the cleanest solution you can have. Ideally, you want to do everything under the same kind of framework. Uh, yeah, but at least at first sight, it needs sort of more consideration on how this can be done.
Cool. So that was the main paper that you worked on at for ICLR. There are some others that your team and colleagues have worked on that we wanted to talk through. Any particular one you want to talk about first?
Sure. I mean, I can talk about one that that I have thought a little bit about as well. So the first one was like a TTN, domain shift aware bus normalization in test time adaptation. Um, and sort of basically this comes from the perspective that at test time, or when you deploy an actual model, sort of distribution shifts are kind of natural, right? So you can if you consider sort of a continuous stream of data, you train on a specific set of data, but in practice you might not have guarantees that the kind of test data that you will apply it come from the same distribution. You could think, for example, this ties nicely with a federated setting where you could have like new clients sort of joining in, and maybe they have like a new device, a new mobile phone, and the camera sensor is a bit different, so therefore the images look a bit different and not exactly like the images that you use for training. And yeah, so basically this paper was sort of had a relatively clean idea in that you have this kind of module usually in your neural network, batch normalization, which estimates some kind of mean and variance statistics over your input data set. So, and then the idea is how can we basically do this in a way that is sort of more robust to distribution shifts that can happen. And the idea was that you can sort of simulate after training some kind of distribution shift by applying some kind of augmentation on your existing images, and then you can learn to basically sort of interpolate appropriately between the statistics you have on your clean data and the statistics that you have on your sort of corrupted data. And empirically this turns out to have beneficial kind of effects in terms of performance when you have some kind of distribution shift at test time.
So let me see if I have the idea here. So you want to apply batch norm, but you're experiencing some kind of domain shift. And so it sounds like you're applying batch norm to the shifted data and identifying how those parameters are shifting, and then applying that same shift to the data that you know.
Well, the idea is that Batstorm has this scale and shift to sort of move like standardize the data. But of course, if the data comes from a different distribution, then this scale of shift doesn't really standardize the data anymore. But if you simulate kind of these effects a little bit during training, you can find like a more robust kind of mean and variance to standardize your data against.
Are you assuming that you know how the domain is going to shift at training time?
Yeah, yeah. So the authors have what they call this kind of post-training phase. So first you train normally, batch normalization as usual, and then there is the post-training phase where all of the parameters are frozen, and then you just learn, a single coefficient per kind of channel in batch normalization that determines whether you should use, how much of the original kind of statistics you should use, and how much of the sort of statistics at test time you should use. And how this kind of interpolated coefficient is trained is by sort of simulating distribution shifts at by doing like specific augmentations on your data set. But then when they evaluated this method, you don't necessarily need to use the exact same augmentations. Of course, if you do, then you have more guarantees that the performance will be good. But empirically, um, this work showed that you can still get better performance than when you use just the statistics that were estimated based on just clean data.
Okay. Interesting. Interesting. So there were also a couple of papers related to scheduling. One was robust scheduling with GFlow nets, and the other was neural DAG scheduling. Can you talk about those?
Yeah, of course, of course. Basically, this is more from a sort of combinatorial kind of optimization perspective. A way to think of this is like, let's say, some kind of compiler where you have a specific set of instructions or a computation graph that you want to evaluate. And then the point is, okay, how do I schedule the operations that lead from input to specific output? Um, and the idea here is ideally you want to learn this kind of schedule that happens for these operations in a manner that sort of you know adheres to the specific kind of computation graph that you have, maybe the specific hardware that you have, so that you can sort of minimize latency. Sort of then there is these two works. The sort of first one, the neural DAG scheduling via one-shot priority sampling. Um, Basically, there the authors use like a previous sort of in-house method proposed by Qualcomm, the topoformer, to learn sort of representations over this kind of directed acyclic graph, this DAG over computations, and then they learn some kind of parameterized policy on top to provide priorities for all of these nodes in the graph. And then the second one, the robust scheduling with GFlow nets, basically still attacks sort of scheduling, but from a different, slightly different perspective, in that sort of evaluating how good the schedule is can usually be very costly because you have to run that specific schedule, and if that is a schedule over, for example, training like a trillion parameter model, that is not something that you can very easily evaluate. So there's this whole set of heuristics people try to use. um, and the idea of this work is that you can basically pick a reasonable heuristic, and then you can sample schedules proportional to the reward that you get from that heuristic. And if you can sample diverse kind of schedules from that, then you can try and see, okay, like some of these might correlate well with the actual task at hand, and might perform well actually in practice, compared to just picking, let's say, the top one from the according to the heuristic, which depending how off the heuristic is with respect to the actual task at hand, might not do as well.
Okay. Okay. And then you've got one composite slice transformer. What's that one trying to do?
Exactly, exactly. So this is also a very, very good work dealing with how you can basically speed up the attention mechanism in transformers. I mean, that is like one of the main sort of computational bottleneck in that it scales quadratically with respect to the sequence size. So what this work sort of does is it somehow decomposes this kind of attention mechanism over a sequence into a local attention and a global attention part. Sort of, let's say that you have a specific sequence, then you split it into, let's say L slices, and then you do kind of local attention, between the elements of the slice, and then you use some kind of aggregate result of that to then do global attention between these slices. This paper then shows that basically instead of now scaling quadratically with respect to the sequence size, you now scale basically quadratically with slice size and sort of linearly with respect to the number of slices, and which is an improvement upon quadratically.
Without much performance loss?
Exactly, without any performance loss. Sometimes actually there was even improvements in performance.
What's the cost then?
You could think of, if there is no overfitting present, right, and you have enough data, then probably you will have some kind of performance loss by doing this. But at least on the tasks that the authors here considered, uh, maybe there was some overfitting kind of present, and that's why doing this kind of decomposition leads to sort of better performance. Having said that, the authors do show that, I mean, there are like other methods that try to kind of make the attention mechanism more efficient. There are some guarantees of this method that this is more flexible than prior methods. In terms of how much can they approximate the full attention.
And then finally, there's a paper, wireless network ray tracing, YNRT. That one is attempting to apply ray tracing to do channel modeling for wireless.
Exactly. So it's actually quite interesting way to think about this. Like, so you have a specific channel that you want to estimate, and then how you do it is you sort of first construct like a 3D representation of the environment. This work deals with sort of indoor type of environments, and then you can estimate like channel characteristics by sort of positioning your sender and receiver within that environment, and then the sender sort of sends multiple rays which they sort of propagate according to the environment and then are received at the receiver side, and then you can basically apply ray tracing kind of methods to see how they sort of interact with the environment and the surfaces and things like that. And one neat idea is that in doing it like this, you can sort of combine um, this method with sort of nerve type of models. Like basically, you can learn to represent this whole thing as a sort of a continuous type of function neural network, where you take the coordinates and see how do those affect the actual propagation of the signal.
Got it. So the nerf part is what's new and interesting here. The ray tracing approach is fairly standard for these kinds of simulations, right?
Yeah, I mean, one of the main benefits of having this kind of differentiable model is of the wireless channel is that you can do some kind of neat applications such as like user localization, right? So you can identify where a user is actually on the environment.
Interesting. Interesting. Awesome. Sounds like a lot of really interesting papers. Kind of going back to your own research, what's next or looking forward for you? What are you most excited about taking on?
Yeah. I mean, federated learning is something that I'm sort of quite passionate about. So there is this, federated learning, typically now relies on some kind of, specific kind of properties that, might be easy to have in practice or might also not be easy to have in practice. Now, first of all is you need access to label data at the sort of edge, right? So if you have some kind of application like keyboard autocomplete, it's easy to have like access to label data because the user sort of corrects, okay, this is like the word I wanted to type next. But if you have something more general, let's say I don't know, like image categorization, right? So it might be relatively hard to ask the user, okay, label this image for me so that I can train a model on. So then how can you sort of basically bypass this kind of constraints? And furthermore, like federated learning, as you said, you train on device, so you don't want to drain the battery. So what actually happens is that usually you train when you are connected to Wi-Fi and on battery like plugged to the wall. And ideally we want to move to some kind of direction in the future where you can lift both of these constraints. Like if you have a very efficient kind of on-device training pipeline, maybe you're fine with just doing it on battery. And if you have like a very compressed kind of communication channel between the server and the client, you can just communicate via mobile data.
Yeah, I continue to hear a lot about the federated learning space evolving. It sounds like there are a lot of interesting kind of avenues to explore there. Christos, thanks so much for taking the time to share a bit about your paper and the work that your other colleagues at Qualcomm are doing.
Yeah, no, it was a pleasure being here, and yeah, thanks a lot for the very interesting questions, Sam.